So I'd like to talk about some software that I helped develop called CASTEP. We'll talk about what it is briefly, but really I'm asking the question whether it's possible to have perfectly portable performance, thinking particularly about accelerators and heterogeneous computing. So first, a little word about what CASTEP is. CASTEP is a software that aims to predict the properties of materials. Properties like, does it conduct electricity or not, or heat, how chemically reactive is it, things like that. Can we predict the results of experiments when they measure various spectra? And the properties that we're interested in are normally governed by electrons. So electrical conductivity is an obvious one there, but many of the chemical properties and mechanical properties are governed by the electrons, which means that we have to use quantum mechanics to do that simulations. Now, if you're a physicist, I have to apologize. That's all the quantum mechanics you're getting today, so I'm sorry about that, but we can talk later if you'd like to know more. The key idea is that the behavior of the material should not be an input, it should be an output. So we want to be predicting the behavior of materials, and really we want to use this as a tool to design new materials with new properties. So we need to be confident about the physics, but we also need to be confident about the software. So CASTEP has got a reasonable pedigree. It's approaching 40 years old as a total project, but it was rewritten about 20 years ago to be what I've called here super, which is scalable, user-friendly, portable, efficient, and robust. And which is to say that the original version was not very many of those things. It's written in modern Fortran, meaning Fortran 2008, and it's also parallel, so you can run it in serial, but it's also parallelized using a combination of MPI and OpenMP. If you're not familiar with those, it's not actually important to today's talk. Things you might care slightly more about if you have users. It's an academically developed code by York, Durham, Warwick very recently have come on board, and Oxford and Cambridge and STFC. And obviously I'm at York, and Durham are also in the N8. We have people from Durham organizing and being part of this. It's free to academics worldwide. It has been for 2 years now. It's dual license, there's a commercial license, but for academic and in fact non-commercial work, it is free. And for today, I'm going to focus on a new challenge, new-ish, which is we want to be able to use accelerators, particularly GPUs. And I thought that this might be particularly interesting today because we have our new N8 Tier 2 facility called BEAD, the patron saint of scholars and, let's say, research software engineers. And it delivers most of its performance through GPUs. Those of you who know your history of high-performance computing may know a saying from Seymour Cray, who founded Cray, which is that if I want to get a serious amount of computing done, I would rather have 2 strong oxen than 1,000 chickens. And with GPUs, this is even more true. In fact, I would say when you're looking to get performance from GPUs, you don't have 1,000 chickens, you have 1,000,000 gnats. So a GPU is many, 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 many things that can't do very much each. And somehow you have to train your gnats to all fly in the same direction and pull you where you want to go, which is quite challenging. There are various software technologies available to do this. Probably the one that gets the most press is CUDA. CUDA is a proprietary software technology by NVIDIA. It only works with NVIDIA GPUs by design. And there are only a handful of CUDA compilers for C, C++, and there is only one for Fortran. So with my CASTEP hat on, that ties me into a hardware vendor and a software vendor, and the hardware vendor bought the software vendor. So I am now tied into NVIDIA for hardware and software. And we're reluctant to do that. That doesn't sound like portable, sustainable performance to us. It also means completely rewriting your code, and CASTEP is about 500,000 lines of code. So we'd rather avoid that as well. OpenCL is another option. It's an open standard, which is quite attractive, but it's relatively low level and involves you at various points trying to make your code look a little bit more like a shader than some of us would like. So what I'm going to focus on is the OpenACC, Open Accelerator standard, which is slowly coming together with OpenMP. So that's what I'm going to focus on. Now, OpenACC is directives-based, which means that you take your source code and you basically add some lines which look like comments to your compiler, but are actually hints about the nature of the code and how you would like to use the GPU to accelerate that code. There are also some libraries available. This is not so portable, but there are some fairly standard ones. So for NVIDIA GPUs, there are QBLAS and QFFT, which have very familiar looking maths and Fourier transform interfaces. If you've ever used those for a CPU, perhaps for the MKL library or OpenBLAS or FFTW, then you'll be very familiar with these. It's very easy to interface to them. And there are some slightly more esoteric ones like the Magma library, which also are good. So with the combination of directives and libraries, you can actually get quite a long way. This is probably the most technical physics slide I have, which is just to say that the workload of CASTEP is often in applying a particular matrix known as the Hamiltonian matrix. There are 4 major contributions to it, and 2 of those contributions I've highlighted in blue. They involve Fourier transforms, which is why I mentioned them on the previous slide. And if you're doing the kind of calculation that makes use of the 4th term here, then actually the FFTs take about 95 to 99% of the entire runtime, which is a pain as a physicist, but it's actually really good if you want to use a GPU, because that means that you have a fairly well-defined computational kernel that you can focus your effort on. It's not one big FFT, it's typically millions of short fast Fourier transforms. They're 3D transforms. So what I can do is I can use my directives, my OpenACC, to tell the compiler, please offload this to the GPU card. I can use a library FFT that is aware of the GPU's QFFT in this case to do the FFT, and then I tell OpenACC to drag the data back. And if I do that with one of my benchmarks, I haven't got time to go into what this benchmark is or why, but it's a standard benchmark we use. I find that my speed up on, actually this was on Summit, which is very like Bead, was about 6 times. So just doing this gets me a 6 times speed up in my total calculation time. So that's not bad at all. But I happen to know that my FFTs are dominated by the memory bandwidth. And if I look at what's possible for the memory bandwidth, this looks a little bit disappointing, actually. So a 6 times speed up is good, but it's using less than half the speed up that I would expect from just looking at the memory bandwidth that's available. So what's going on here? And if I look, what I'm finding is I'm getting the correct answer, and it's 6 times faster, but the time that I'm spending in my API, and this actually is on an NVIDIA GPU, so I have a CUDA API as the back end, about 60% is launching GPU kernels, and about 30% is synchronizing CUDA streams. In other words, I'm spending a lot of time telling the GPU to start work and waiting for various bits of the GPU to finish their work. I'm not spending a lot of time with the GPU actually working. So I'm not occupying the GPU enough. It's hungry for more data. It's hungry for more work to do. And I can illustrate that with a timeline. For the purposes of today, time is going left to right, and the colored areas are where the GPU is doing something, and the blank areas are where it's sitting there not doing anything. So you can see that quite a lot of blank areas, quite a lot of starting and stopping and waiting around. So what I did, and when I say I of course mean my PhD students, they refactored the OpenACC so that instead of having these directives just on lots of little loops and lots of different areas, they fused them together to make bigger areas that could be offloaded to the card. And actually, this wasn't actually all that difficult. And they also changed the FFT, so instead of launching 1 or 2 at a time, they batched them together into bigger chunks. And this is my new timeline analysis on the GPU cards. You can see that now I get very solid blocks of color and different operations occupying the card almost consecutively. And now we find instead of our 6 times speed up, we get a 14.5 to 15 times speed up. So I got a factor of more than 2 extra just doing this. And this now is data from BEAD from this calculation. So that's been a slightly whistle-stop tour. That brings me to pretty much to the end. So I must thank my PhD student, Matt Smith, and an RSE at the Cambridge Tier 2 facility, the CSD3 facility, Ian Tamaris, NVIDIA, BEAD, Sheffield, and Oak Ridge. And I must thank EPSRC because they also were foolish enough to give me an RSE fellowship, which has funded me on this work. And just want to finish by highlighting a few challenges. So I would say OpenACC is quite a low barrier. If you have C or Fortran or C++ code, it's a low barrier route to getting GPU offload. But getting efficient offload does require a bit more thought and requires you to know a little bit more about the technology. So it isn't as simple as a compiler is, for example, for getting CPU work. And there are still many challenges. I've put a few of them on here, but the one I'd like to highlight are the last 2. So even though OpenACC is an open standard and there's no vendor lock-in, in fact, if you look at OpenACC Fortran compilers, your choice is NVIDIA compiler or GCC collection, I think probably 11 before it's actually useful, which is better than just the CUDA Fortran, which is just NVIDIA, but it's not as much better as we'd like. And OpenMP is coming along, and it now looks, certainly as of the OpenMP support this year, looks like OpenMP might be a possible way forward, and Intel are also on board with OpenMP. So we have support from NVIDIA, GNU, and Intel. That does look like that might be a proper open standard that we can get the whole community behind. And with that, I will finish. Compare the refactored GPU to refactored CPU. We didn't refactor the CPU because what we've done is not refactor the code. We've refactored the OpenACC directives. Having said that, there is some modest advantage from batching FFTs on a CPU, but it's pretty modest. It's a few percent. It's not the factor of 2.5 that we saw from the GPU. The reason is partly that the launch latency, so the time it takes to just launch a kernel on GPU is very high. On a CPU, the model's very different, and it's very low overhead. People are working very hard to support OpenMP and with Fortran, and yes, that's true. And Intel have their One API initiative, although for Fortran, One API just basically means OpenMP with Fortran. So One API is a brand, but it's little more than existing things. Just one. Yeah, so we worked very hard in 99. I said we started the rewrites, but what we actually did is we rewrote it on paper for 6 months. So we wrote a design spec. And it was very painful in those 6 months, especially as that was 6 months of the 4th year of my 3-year PhD. But it was worth it. So we gained both from it being the second time that we'd been involved in it. I was mostly a user developer for the 80s code. That was my PhD starting. But we'd all realized by then that it needed a rewrite. And that was really my first introduction to proper hands-on software engineering. I did that I did a 1-year master's in computer science. So I learned about software engineering then, but I didn't use it very much until the rewrite. But the OpenACC has been bolted on. In fact, the OpenMP was bolted on. It was MPI parallel from the start of the rewrites, but all of the threading and all of the GPU stuff, of course, has been subsequent to that, but has not required a proper rewrite. This is the same test case we used on Summit. But the reason for that is because we're doing a lot of Fourier transforms, and in a large machine, they'd be parallelized. Parallel FFTs are a pain to scale. So getting those to exascale is very difficult. Actually, Matt Smith, that's the other half of his PhD project. So I'm pleased to say we now can scale an order of magnitude better than we used to be able to. but a 10-minute talk couldn't cover that as well. And then there are fewer RSE points there. But yeah, it's not a problem on Bead. If you want to know where the challenges are, I would say they're really in how you handle how many MPI processes talk to your GPUs. So there's a big question of how you occupy the CPUs versus the GPUs. In other words, how to use the whole of Bead. It's very tempting to just focus on the GPUs, but it does have some Power 9 CPUs. They're not the beefiest in the world, but you do get 40 odd cores each. And how do you handle the communications? Can you involve the GPUs in that, or does it go through the CPU, or how do you do that? And longer term, I think that is a challenge. So are we saying long term with exascale that we're going to just make the CPUs really stupid basically and not do anything except a bit of the IO? Or are we going to have a proper heterogeneous computing solution where the CPUs do some things well and the GPUs do some things well? And that's the approach that Magma have taken in their library. And the jury's out, really.